Hi, this is our case study project CHM260, and this is our group members.
Okay, the first is introduction of AAS. What is AAS? In chemistry, the atomic absorption spectroscopy or AAS is a technique for measuring the concentration of metallic elements in the different materials. As an analytical technique, it uses electromagnetic wavelength which coming from a black source. And then, distinct elements will absorb this wavelength differently. It will give the different picture concentration for a specific element there is whatever material or liquid is being tested. Okay. Next, we're going to explain about the atomic absorption spectroscopy. First uses of the atomic spectroscopy was for cost-effective ideal solution for the analysis amounts of metal in the samples. Then, by using gravimetric methods, it generates a high degree accuracy results with affordable cost. Then, the purpose for the atomic spectroscopy was primarily for determination of metal trace in many types of samples composed of organic and inorganic matrices. Then, the atomization helps to detect elements by emitting their characteristic wavelength that absorb from their different radiation.
Okay, next for the AAS principle. AAS principle was used to the flame test in the quantitative methods analysis. And for the characteristic flame color, it can be observed to the alkali metal salt that's strongly heated in the Bunsen flame. So we can determine which one the elements that had used for our
Three technique methods included in atomic spectroscopy. First one is atomic absorption spectroscopy, the second one is atomic emission spectroscopy, and lastly, the atomic fluorescence spectroscopy. But in this term, for the first one, we had used this because it was from our
Assalamualaikum everyone. So today I will present about the atomic absorption spectroscopy AAS experiment. This is special for our beloved lecturer, Mrs. Nur Hafiz Arbain. And this experiment will be presented by Latika Fadil, my friend, and me, Alia Asmi. So I present about the first methodology and second about the analysis. So next we will go to the methodology. What is methodology? First we have to know the apparatus and chemicals. For the apparatus, we use 100 ml, 25 ml, and 10 ml of volumetric flask. Then we use 50 ml of aluminum flask, glass funnel, 1 ml of glass pipette pump, spatula, and hood lid. For the chemicals, we use 0.025 molar calcium chloride, 30% hydrogen peroxide, and milk sample. Next, you want to know how the sample.
Let's begin with the sample. Weigh 1.0 gram of milk into a 50 milliliter Erlenmeyer flask. Perform in triplicates. For the sample blank, weigh 1.0 gram of DD water instead. Do this only once. Inside the fume hood, add 5.0 milliliters of concentrated nitric acid and 1.0 milliliter of 30% hydrogen peroxide to each sample and sample blank. Please note that the fumes created by the reaction will be very toxic. Set up the hot plate in the fume hood and heat the flasks at medium heat. Swirl occasionally. Your solution should change from cloudy to dark orange brown to clear pale, while your blank should stay clear. If your solution is still orange brown after 20 minutes, add an extra 2.5 milliliters of nitric acid and 0.5 milliliter of 30% H2O2 and continue to heat. It is possible to obtain a clear yellow solution if you put an excess amount of nitric acid, but it does not affect the result. After heating, transfer the samples and blank separately into 100 milliliter volumetric flasks. Rinse each Erlenmeyer flask with DD water and add it to the volumetric flask makeup to volume. Invert a few times to mix. Next, pipette 1.0 milliliter of each sample or blank to corresponding 10 milliliter volumetric flask. Add the appropriate volume of 2.5% lanthanum oxide solution to each flask to obtain a 0.5% final concentration, and make up to volume with DD water. Invert a few times to mix. During the wait time in the sample preparation steps, you can begin preparing your standards. First, dilute the 0.05 milliequivalent calcium chloride standard solution by pipetting an appropriate amount of the solution into a 100 milliliter volumetric flask labeled 100 micrograms of calcium per milliliter. Add DD water to volume. Invert a few times to mix. Then label the 25 milliliter volumetric flasks with concentrations 0, 0.5, 1.0, and 2.0 micrograms of calcium per milliliter. Pipette the required amount of the 100 microgram calcium per milliliter solution into each of the 25 milliliter volumetric flasks. Then pipette the required amount of 2.5% lanthanum oxide solution to obtain 0.5% lanthanum oxide in the standards. Make up the volume with DD water and invert to mix. All samples and standards will be measured using the atomic absorption spectrophotometer. Bring your samples and standards together with DD water to the instrument. Your TA will briefly show you how to ignite the flame. You must assemble the sample slot, ensuring that it is screwed on tightly. Otherwise, you will observe leaks when DD water is being fed into the instrument. Turn on power switch of the instrument. Then turn on the acetylene gas tank. Next, turn on the airflow. Adjust the airflow and fuel to the appropriate level. Turn the control to air while lighting the flame with the lighter. Turn the fuel to on position. You should observe a nice blue flame about 2 inches tall. Please note that it is important to follow the proper order to ignite the flame, or you will create a lot of ashes but fail to ignite the flame. Now the instrument is ready. Place the sample feeding tube in DD water first until there is a constant violet blue color. Pay attention if there is any leak around the sample slot. Zero the spectrophotometer by pressing the AZ button while feeding DD water. You should start with the standard with the lowest concentration. Dip the feeding tube into the standard solution. The flame should turn green. Record the reading and dip the tube back in the DD water to rinse. Continue with all standards, then the sample blank, and finally your samples. When completed, flush the sample slot with DD water. Your TA will turn off the instrument for you. Discard your samples, sample blank, and standards into containers labeled lanthanum oxide wastes.
That's it. Next, we'll go to the analysis. We want to analyze this experiment. Let's say the graph. We have two graphs. First graph is explaining about the absorbance and concentration readings of calcium in standard solution. So we have 5 samples here, and that is the concentration and absorbance values. The second table is about the absorbance and concentration readings of calcium of the known pH. Okay, we have 5 pH used in this experiment: pH 1, pH 2, pH 3, 4, and 5. Next, we go to this is the graph: absorbance versus concentration of calcium in standard solution. So absorbance is directly proportional to the concentration. That's what we get. Oh, sorry for my mistake. Then the graph of concentration of calcium versus absorbance. Next, we go to the calculation. We have to know the weight of calcium chloride with hydrogen peroxide powder to prepare the 1 ppm of calcium solution. So you get the 0.037 gram of calcium chloride and hydrogen peroxide. In the calculation of standard solutions for 20 ppm, 15 ppm, 10 ppm, and 5 ppm, we will use the formula M1V1 equal to M2V2. M is known as molarity or concentration, and V is volume. Next, we will go to the discussion. For the discussion, first is the interpretation of result. Dilute the 50 ppm stock solution to make 20 ppm, 15 ppm, 10 ppm, and 5 ppm standards. A blank solution distributor is used with the AAS instrument to accurately read the calcium concentration. Second is the relationship between absorbance and concentration. It has also been shown that the higher the concentration, the greater the energy absorbed to excite the electrons in the sample. Next, we will go to the interpretation of graph. Theoretically, the plotted line diagram should yield a straight line with r squared equal to 1, but the actual experiment yielded a straight line with r squared equal to 0.9931. The measured value does not deviate significantly from the theoretical value, but it may be because the calcium salt weight was 0.038 milligram instead of exactly 0.037 milligram. Next is the additional value for the viewers. Is the factors other than pH that affect the human digestive system. In addition to pH, there are several factors that affect the human digestive system. In addition, it has an optimum temperature and pressure, which is one of the factors affecting the human digestive system. Thank you.
For the conclusions, in this experiment, we can conclude that we learned more in the correct procedure of how to operate the playing of the AAS instrument, which needed to follow to avoid the fidelity of the experiment according to the should be in instruments. We can also plot the standard calibration curve for the determination of the samples and obtain the absorbance and the concentration solutions that have been used in the different standard solutions concentrations. Last but not least, the amount of the elements in the samples was determined using the standard calibration curve that has been plotted by Excel or something app. And then for the 10 times dilution of the HN3, we can observe some goes to the other standard solution. That's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. In recent years, the technology used in chromatographic analysis has greatly improved. Advances in this area have led to the common use of high-performance liquid chromatography, a laboratory technique that allows for the very efficient separation of small amounts of the components of a mixture. The technique has essentially the same operational basis as liquid chromatography, but HPLC allows for far better separation of the components of a mixture. The column in an HPLC instrument contains tiny particles of only about 5 micrometer diameter, ensuring a very large surface area to which molecules may adsorb. These particles comprise the stationary phase of the chromatographic system. Because these tiny particles are so tightly packed, the mobile phase solvent must be forced through the column under very high pressure. A detector and a computer are connected to the HPLC instrument in order to signal when eluents are coming off the column and fractions should be collected. Identification of samples is carried out by comparison of their retention times. A known amount of a known compound, a standard, is injected. The retention time is recorded and the area under the peak can be calculated. A sample containing the same analyte is then injected under the same experimental parameters. If the analyte is the same compound as the standard, then they should give identical retention times. The ratio of peak areas should give the amounts of components present. Reverse phase partition chromatography in HPLC employs a polar mobile phase and a non-polar stationary phase. This is the most frequently used form of HPLC. Other modes of liquid chromatography include normal phase partition, non-polar mobile phase, and non-polar mobile phase and polar stationary phase, absorption, ion exchange, and size exclusion. The column used in this experiment consists of a layer of an alkane C18 chemically bonded to the surface of very small silica particles. The operating instruction is as follows. For sample preparation, first use a syringe and a filter to transfer sample 10 to 20 ml into a vial. Type of filter is SRP15 0.45 mm. To prepare mobile phase, filter the mobile phase. For methanol, water, buffer, and acetonitrile (ACN), use membrane filter. Use ultrasonic cleaner model UC05. For sample injection, click single run acquisition, insert syringe and load. inject sample and turn down. Select control, extend run to a certain minutes. And then select report, view, method custom report. Then print results. And for cleanup process, click LC Setup Assistant. For mobile face, B, C, and D, wash with ACN. Click 100% ACN. For buffer, wash with water, click 100% water. Lastly, switch off the instrument.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Azimah binti Muhammad Asabri. Now we're going to talk about what we can understand about HPLC and its properties. HPLC has become one of the most powerful tools in analytical chemistry because it has the ability to separate, identify, and quantitate compounds that are present in any sample that can be dissolved in liquid. It was used in a variety of fields in science like chemistry, medicine, forensics, and etc. There are two types of HPLC. First is normal HPLC and reverse HPLC. Next, we're going to talk about the differences between normal HPLC and reverse HPLC. Normal HPLC is a chromatography technique that uses a hydrophilic stationary phase. It evolved in the 1970s in the form of liquid chromatography. It has poor reproducibility of retention time. This is because there is the formation of layer of water or protein organic solution. Because the hydrophilic stationary phase might have reacted with hydrophilic components in the sample mixture. Because of this, the column is easily damaged. So many scientists didn't use the normal HPLC as much as we thought. The stationary phase that was used in normal HPLC is a polar compound like pure silica, and the mobile phase is either less polar or non-polar at all, like chloroform and hexane. Because the stationary phase is polar, the non-polar components of the sample will elute first. So to increase the elution time, the polarity of stationary phase might have to be increased. Now we're gonna see the reverse HPLC. It is a chromatography technique that uses a hydrophobic stationary phase. The reverse HPLC is a recent evolution of HPLC. It has higher reproducibility of retention time compared to normal HPLC. This is because there is no formation of layer of water or protein organic solution. Hence, the column is hard to damage and is broadly used around 70%. The stationary phase that we use is a non-polar, like modified silica with hydrophobic chain of components. The mobile phase is a polar, which is water with acetonitrile. Because of the stationary phase, the polar components of the sample will elute first. So to increase the elution time, we can decrease the polarity of stationary phase by adding water. Okay, now for the result, we can see the caffeine standard. First, we're going to take a look at caffeine standard. The elution time is, we got 1.375 minutes, while the area around 96.4734. And the concentration for caffeine standard is 0.1 milligram per milliliter. First, we have to calculate the RF because we're going to use RF to calculate the concentration of our sample. We got our RF by 964.734. Next, we're going to take a look at sample 1. The elution time is 1.381 minutes, while the area is 27.9752. And now we're going to calculate the concentration of caffeine in ppm. The formula is the peak area of caffeine in the sample going to be divided by the RF, which we already calculated by using caffeine standard. After we enter the value, we got the concentration of caffeine in sample 1 by 28.998 ppm. Now for sample 2, we're going to use the same equation, and we got around 48.83 ppm. And for the last one is the sample 3, and we got 119.17 ppm. The reason why we run the sample 3 times is to get the more accurate result. Next. So, as conclusion, the polarity of the stationary phase and the mobile phase is the crucial factor to determine the elution time. Most importantly, the polarity of stationary phase, because the elution time for the components in the sample to elute will determine by the polarity of stationary phase, whether it's high or low. And the distance between the peaks will also determine by the elution time. And each component of HPLC has its own role to make sure there is no error while finding the components in our sample mixture. Like degas, like we can take degasser as an example. It removes the bubbles or any dust that form while we doing our experiment, because the bubbles will give impact in our peaks, which there will be a small peaks, which is an error. That's all from me. Thank you.